Well, howdy there, partner. Just trying to put on some different stuff, like use some of the clothes in my closet since I don't get to go out a whole lot at this point. So, hence, doing my own little dress up day there, cowpokes. Gonna try to wear this cool hat I got for the Spirit Day in January. I'm gonna wear this jacket I found at Kohl's at one point. It's weird to think of things like going to Kohl's as being something in the distant past, but hey, we're at that point. So anyway, as you might expect, I'm back. I'm here to work through the next lesson. And in fact, this is kind of a special lesson almost, if you will. This is the final lesson of this unit, the second major full unit of Calculus BC as I teach it, which means that we're pretty close to the end. In fact, as things are written right now, I only have one formal lesson that's going to follow this one that kind of exists in its own little, I want to call it its own little unit, I want to say. And so for this point, we're almost at like our second to last full lesson. There may be a few other ones that'll pop up, and obviously I'll have some review tools for you before that AP exam and before any sort of final exam we might take, although I have a feeling that's not going to be a big old formal thing. But at the same time, I do want to give this last big topic kind of its due as we start to wrap up this idea of Taylor and Maclaurin and power series approximations and the idea of this whole concept and world. So, having said that, like this lesson, as it's titled, is titled Error Bounds, which is going to be based on accuracy. We're going to be talking about how accurate the Taylor and Maclaurin series that we come up with actually are. And it's kind of an interesting thing to bring up, simply because it's something that kind of gets forgotten, I think, in the process of computation, like learning to compute all these different things and calling them series and calling them polynomials. We sometimes forget the purpose behind these things that we've developed, this entire area of calculus we're developing. Now, having said that, before I jump fully in and delve into that idea of approximation, let me just point out that teaching a lesson like this one is basically a sort of nightmare. This is usually considered probably the most, I don't know what the word is for it, like the tough to understand topic. It's just kind of weird. I think that's the best way to describe it is it's weird. So I've tried to redefine this and kind of move some stuff around, add a few extra examples, mix in triads as well to try to make this understandable in a format in which I can't actually respond to your questions and clarify as things go. So when I looked at it this morning and was going through the problems, I felt like it was going to go really fast. So I tried to scale it back and increase the number of examples so that way I could support you as best I could with that. I've also gotten rid of a couple theorems. In fact, if you're into like taking a look, there's a couple theorems that are out there that I'm just not going to go through. Not because I don't think they're important, but because they aren't really relevant. And if there's a format in which I shouldn't be trying to inject extra stuff into it, I'd say it's this online education platform. So instead, I'm going to try to simplify things and try to be as clear and concise as possible while giving you ample examples while dressed like a cowboy. So having said all that, let's jump into the concept of error bounds. So as we begin to discuss today's topic, the final one of this Taylor and Maclaurin unit, I want to remind you that although these things might be something that are just kind of computational in nature to you, they're a thing that we use derivatives to generate, or we use power series or manipulation techniques to generate, the truth is these weren't designed to be some sort of fun little mathematical game. We weren't trying to play algebra. The idea was we wanted to find some way to connect functions that behaved, we'll say a little bit more challengingly, with polynomials, which behave just okay. Like they're pretty good to work with. And although that in itself is a nice, noble goal and definitely something valuable, I mean, anytime you can turn something as complicated as a transcendental function like e to the x into a polynomial, that's got to be a good thing. But really, the value in doing that wasn't, for at least for early mathematicians, wasn't to just do it. It wasn't to be able to say, ha, look what I did. It was to be able to approximate values of those transcendental functions better and quicker and more accurately and more easily. So let me point that out and kind of start there just as kind of a point of context. So let's start with a function we know well. We know that cosine of x is actually going to be equal to, this is one of those functions that has an infinite radius of convergence. It's actually equal to 1 minus 1 over 2 factorial x to the second plus 1 over 4 factorial x to the fourth minus 1 over 6 factorial, I think that's 720, x to the sixth, and then it goes on for a while and then we add to it the general term, which has a toggle because the sign keeps switching. It's x to the even powers, and then all divided by the even factorial. And so there is cosine of x. So what we have on this side is the original function, that transcendental function, and then on the right we have its polynomial version. Now, one of those theorems that we're not going to get to go through talks about the fact that this is a special thing and how Taylor polynomials are particularly special types of power series. Not going to go that route for now. Instead, I want to point out that the real value in something like this is that we can actually compute values of this function using this polynomial. So let's start with something first. Let's just be honest. If I ask you what the cosine of 1 is equal to, you could, of course, pull out a calculator and you could tell me. So let's do exactly that first. Cosine of 1 says 0.54030. And actually I have it on my notes, so I'll write it down. Oops, I put an extra one in there. 2305 ... Okay, so there is the value. It would obviously extend on forever. This is an irrational number. Now, having said that, keep in mind that although I could just as easily switch the window and get this value, the truth is early mathematicians did not have that luxury. They didn't have scientific calculators. They probably had an abacus, but even then you couldn't compute something like cosine of 1, as far as I know about abacuses and abacus. So having said that, they didn't have the option of just finding out the value. If they wanted to know what the value of cosine of 1 radian was, they would have to use approximations. They'd pull out some sort of table or book that had some massive chart that told them values of cosine, but more likely, that book had to get those values somewhere too. So what they would do is they would approximate instead. They'd point out that cosine of x, or in this case, let's just go cosine of 1, is approximately equal to, let's start with, p sub 0 of 1. P sub 0 of 1 would be equal to just 1. So of course what this says is if we just use the first term of the Maclaurin polynomial for cosine, we get an approximation. Now 1 doesn't look so good, so naturally they wouldn't settle for 1. They'd probably start using additional terms. So let's take, for instance, p sub 2 of 1. That's going to be equal to 1 minus 1 over 2 factorial times 1 squared, which is just 1 minus 1/2, which is 0.5. And hopefully you saw just what a significant addition that minus 1/2 term was. All of a sudden 0.540, it's looking pretty generous, looking pretty good. Let's try another one. If we try cosine of 1 and we approximate it with p sub 4 of 1, that's going to be, of course, 1 minus 1/2, but then plus 1/24. And if memory serves, that's 24 over 24 minus 12 is 12 plus 1. I think that's going to be 13 over 24. And I wrote down this value for myself later. It's 0.54166 ... Notice we're even closer now. 0.540, 0.541. And the idea is if we continued this process, I'll only do it one more time, don't worry, I'm not going to bore you to death with this, but if we just kept plugging in 1, in this case it's pretty simple, we'd get 13 over 24, and then minus 1 over 720, and let's go ask Desmos really fast what that value is. So 13 over 24 minus 1 over 720, and actually I think I set this up so I could actually say p sub 6. What did I just do? There it is. 0.540277. And what my point is obviously the more terms we add, the more accurate we get. Our estimate gets pretty close. And because we have the advantage of being able to look at the actual value of cosine of 1 written out to pretty much whatever decimal accuracy we want, we can see just how powerfully we're improving our estimates by adding even just the 6th degree term. So the idea is our approximations obviously get better and better the more terms we add. The problem is, because early mathematicians and workers of calculus didn't have the ability to compute these things all the way through, they couldn't settle for just getting an approximation and going, okay, well I can see how close it is. What they wanted was some way to guarantee how accurate a particular estimate was of a particular function value. So for instance, a question that one might ask would be, how accurate is our estimate of cosine of 1 going to be if we use the 6th degree Maclaurin polynomial? How accurate is the estimate that's given by the 4th degree Maclaurin polynomial going to be of cosine of 1? In other words, the question is of accuracy. And in fact, the question of accuracy is going to be about what's the biggest mistake we could make. Because if we knew the exact, what's the word I want here? If we knew the exact error on a particular estimate, then we wouldn't have any sort of issue estimating at all. We just add that error to whatever our estimate was and we get the right answer. The truth is, all we can do basically is create a sort of mathematical umbrella, if you will, and say, hey, based on this information, we're going to figure out the biggest that our error could ever possibly be based on things that we know. And then we'll be able to say that our actual approximation is within this much of the correct value. Now, I realize that's not necessarily doing a lot or explaining a lot. Obviously, it works a little bit better in class, although I will add my little umbrella here, just so that way, boom. You can imagine Mary Poppins flying on her little umbrella. Boom. There it is. So in any event, like, the idea is we're trying to find some way to cap the accuracy, or to be able to measure sort of the accuracy of a particular estimate using a Maclaurin polynomial. So as it says on this next page, again, I'm probably just getting lost in the attempt to explain something that's not easy to explain. The question is, how close do we get with a particular estimate? So typically this is what you're going to see when working through an error-bound problem, is you're going to see a description, or you're going to be talking mathematically about this idea of closeness of a particular estimate with a Maclaurin or a Taylor or something else to the actual function value. So describing all this stuff, we've used this notation before. First and foremost, this is going to be our error. Some places refer to it instead by the name remainder. That's actually what the R stands for, if memory serves. So this error is specifically the error, or the difference between the actual value and the approximate value, when using P sub n to approximate. And it'll be at specifically whatever number we happen to look at. So this is the function value. That's the value we're trying to approximate at. So I'll just describe this as the where. So this is our thing. We're saying the error is equal to this. Now in our this, we have in here, we have the f of the number, which is going to be our exact value. Now of course we're not going to know that. If we knew that, we wouldn't have any sort of need to approximate. So truthfully, everything we do today is kind of a throwaway, but beside the point, it's definitely part of the curriculum. So that's the exact value. We're trying to figure out how close we are to that exact value with a particular estimator. And then finally, we have P sub n of the number, which is going to be our approximate value from whatever the Taylor thing was that we were looking at. So in other words, that's going to be what we would have for our estimate. And so what we're trying to do today is we're trying to figure out what's the biggest that this error can possibly be. So in fact, let's write this with an example using the stuff that we just worked on. So in our previous example, remember we did all this work up here to approximating cosine of 1. We could say that we were interested in r sub 4 of 1, which would be the error when estimating cosine of 1 with a 4th degree Maclaurin polynomial. That error is specifically equal to the absolute value of cosine of 1, since that's our exact value, minus a particular approximation. In this case, it'd be P sub 4 of 1. That approximation that we got when using P sub 4, which was right here. So in fact, you could also say that this is the same thing. It's the same thing as approximating, or taking the magnitude of cosine of 1 minus 13 over 24. So the truth is, that's just kind of stating the vocabulary. What we want to pull out of this, though, is something that goes right here. We want to figure out what goes right there, or there, depending on how you look at it. And these things, the best way I can describe it, is going to be that cap. And it's going to be a cap on the error. some sort of relationship that tells us that in a given approximation, this is the largest that our error could possibly be. This is the furthest we could be away from the correct answer. Obviously, it won't be exact. It's going to be an inequality, just as you see right there. It's going to be an inequality. So we're really not getting something formal like figuring out what the error is. We're just getting a bound for the error. So hence what we're looking for is, of course, what's called an error bound. And as I described on the previous page, I like to think of it as like an umbrella. We're going to find a really big one that covers all of us, that covers all possible errors, and that way we're going to make sure that our error is underneath it, in the right space, and not getting, I guess, mathematically wet. I don't know. My analogy broke down. So there we go. So that's what we're aiming for. So the first one we're going to look at. There are two different error bounds we're going to see, and the good news is the first one is one that we have seen before. It is called the alternating series error bound. So this error bound is only going to work if the Taylor series, Maclaurin series, Power series, whatever it is you're looking at, this only works if that series has alternating signs. So it matches that toggle, one back and forth, plus, minus, plus, minus, plus, minus, or of course, minus, plus, minus, plus, minus, plus. So I said this is also familiar, and the specific reason for that is, as it says here, if your sign is alternating, we can treat it just like an alternating series would. As it says right here, your error when approximating at the number is less than or equal to what I've described as a sub n plus 1. And the truth is, a sub n plus 1 is just code for the next term after the one that has the thing that we're looking for. So this is actually just the same thing we've seen before. It's just the alternating series thing that allows us to bound the sum of the alternating series. They're right up related to one another. The big thing I want to add here is this expression, this next term, is actually called the alternating series error bound. And I should have written this out ahead of time, but I guess my fault. Alternating, yep, and I wrote it wrong already. Just get flustered writing this lesson. Actually, if you want to watch the music video I made, it's not accurate because I had a very poor understanding of the stuff. The textbook that we had before did a very poor job of describing this and didn't even acknowledge the existence of the alternating series error bound, had everything with the other one. But you can watch that video. It is on my YouTube channel somewhere. That's fun. That was my first BC class too. Also the first Frozen movie. So there you go. So anyway, this is called the alternating series error bound. What we're going to be looking to find is what the next term would be, and then we'll use the magnitude of that next term to determine how accurate our estimate is. Now down here, if you're wondering where this comes about, we've already discussed this. We've already done this lesson, so I copied the very nicely written, I will say, description out of the alternating series lesson. I want to say that was notes 28. I think pretty sure it's 28. I might be off by one. But basically that was something that we saw. There was even a proof in there if you're curious about it. This is our option if we have an alternating series. Now I don't want to go back into depth there. I just kind of want to show you what it looks like because I think this one is one that's easier to do than it is to try to fully wrap your mind around. So having said that, obviously if you want to keep looking at this or write more stuff down, be my guest. But I'm going to move forward so you can pause it and then take a look and catch up with us. So here we go. So we've got a couple different problems I want us to look at here. I've got 2 for each of the 2 different types of error bounds plus 2 for each try it to give you as much experience as possible. And I tried my best. I obviously looked over all this stuff and did everything ahead of time, but I haven't grinded through these problems again because I wanted it to be as authentic as I could possibly make it. So in the first example here, it says consider f of x equals cosine of 2x. So keep in mind it's not cosine of x, it's just cosine of 2x for the moment. It then says let p sub 4 be the fourth Maclaurin polynomial for f of x. And then part A asks us to find p sub 4. So p sub 4 is not anything involving error bounds, it's just something we kind of have to do. So thankfully we've already done some good work involving cosine today in this one. So I'll go ahead and just write that out and remind us. Cosine of, no, I'm not going to remind us. Geez, who am I? I can do better than that. I'm going to completely and totally steal the umbrella. Okay, lovely. Okay, let's get rid of the umbrella right there. Okay, so I was going to write the whole thing out again, but no. I'm going to save a little bit of space and time here. Okay, so recall that. We already know what cosine of x is equal to. The reason I bring that up is, of course, what we want is we want to be able to find cosine of 2x. So we can work with this and come up with p sub 4 for cosine of 2x. So cosine of 2x is going to be whatever we get when we plug in 2x to this expression. Now, as a heads up, if we want to do p sub 4 of x, we should only need to plug it into the 4th degree one. So I'm only going to go that far. So in fact, that means I'm going to change cosine of 2x into being approximately equal to 1 minus 1 over 2 factorial times 2x squared plus 1 over 4 factorial times 2x to the 4th. Simplifying this out a little bit, that'll be 1 minus 1/2 times 4x squared. And then the last one will be 1 over 24 times 16x to the 4th. And if we clean that up a little bit, we'll get as our expression that p sub 4 of x is going to be 1 minus 2x squared plus, let's see, what's 16 over 24? I think that's 2/3 x to the 4th. And I'm going to check myself on all these just to make sure that I don't mess up. I did not, or else I messed up this morning when I started prepping for this one. There we go. Okay, so we found p sub 4 of x. A nice little momentary pause of things we know how to do in preparation for the new kind of thing. So there we go. So having said that, the next question that follows is always going to look a little uncomfortable when you deal with it for the first time. The next question then asks us to show that the absolute value of f of 1/2 minus p sub 4 of 1/2 is less than 1/700th. So first of all, the first time I saw a question like this, I was just like, 1/700th? Like, where would that number come from? And then, of course, you have to kind of parse everything that's in here. There's actually not a whole lot to deal with, but having said that, we do have to kind of dig out some information first and foremost. So in here, in this statement, right here, the least important thing is actually the 1 over 700 for the moment. So keep that in mind as we start to look. What's important is to realize a couple different things. First and foremost, I want to point out that the x value that's being plugged in here, did I call it x? Yeah, I think I did, is basically our number that I was describing on the previous page. That's going to be 1/2. We're plugging 1/2 into the function and into the Taylor polynomial or Maclaurin polynomial, so it's important to note that. Second, although it's not stated here, since p sub 4 is Maclaurin, that means the center is 0. That's an important consideration as well. Third, n equals 4, and that's an important consideration because what that means is by recognizing that we're using an approximation of degree 4, that means that we need to consider what term comes next. So whatever term follows n equals 4, we're going to need to use that when we construct this error bound. And obviously we know for cosine that's going to be 6, but you know, for the moment it might be more interesting. It might be a different problem. Okay, so having said that, here's what we're going to do. I'm going to start to attack this thing. First, I'm going to rewrite this. And again, I haven't been able to do this on the full screen with my new bigger handwriting for Brittany. So having said that, let's see if this works. So according to this thing, it's important to note that clearly cosine of 2x's series alternates. So, and I'll just write that in here. So, series for cosine alternates. That's important because if the series for cosine or cosine of 2x didn't alternate, then we wouldn't be able to use the alternating series error bound. So let's just point that out, that of course we're allowed to use this alternating series error bound structure because the series alternates. Now, having said that, according to what we mentioned on the previous page, is that this is going to be the equal to or less than the magnitude of the next term. So whatever term comes after the degree 4 term is going to be the one that we end up digging through. So from here, what I'm going to do is I'm going to start to think about what that next term is going to be. Of course, I'm going to take its magnitude. I only want to deal with the positive part because I want to be able to talk about this error as like a positive value. So having done that, let's think. According to what we've seen here, we have this. Here, I'll change color. In fact, let me change to pink. We have this as our next term in cosine, 1 over 6 factorial x to the 6th. But more than that, we know that if we're doing this for cosine of 2x. That's our particular function here is cosine of 2x. So for us, what that means is that our next term is going to be negative stuff to the 6th over 6 factorial. So having said that, we have to also take into account the fact that we're plugging in 2x because of the fact that it's cosine of 2x. So there's what our next term is going to look like as a function of x. I will clean this up a little bit. That's going to be equal to, it looks like 64 x to the 6th over 6 factorial, which is 720. So there is our value. There's what the next term would be. But keep in mind there's a little more information that we need to include here as well. And I'm actually just going to take care of it myself right now. Remember, we noted that because 1/2 is plugged in here and here, that means the x value we're plugging in, kind of the value we're trying to approximate at for this particular series or with this particular series, is going to be at x equals 1/2. So to find the specific term itself, I'm going to plug in x equals 1/2. When I do, that's going to lead me to 64 times 1/2 to the 6th over 720. Now you may realize why it is that I did this. Like there was a very intentional reason I did this already. We now have in our numerator 64 times 1 over 2 to the 6th. 1 over 2 to the 6th is 1 over 64. Granted, all that stuff is over 720. But what I notice is that the 64s divide out, and we're left with 1 over 720. So what we've just found is what's called the alternating series error bound. And that bound is equal to 1 over 720. What that tells me, what that tells all of us really, is that if you're going to use p sub 4 of x to approximate values of cosine of 2x, then when at x equals 1/2, the largest possible value that error could ever have, the biggest that you could be, the biggest, I was going to say mistake, the furthest you could be away from the actual value of cosine of 2x at 1/2 would be 1 over 720. Now that might not seem like a big thing, except what it does is it allows us to say this. We've just shown that f of 1/2 minus p sub 4 of 1/2, at least when taken as a magnitude, is less than or equal to 1, let me make sure I used that correctly, yes, over 1 over 720. So that's what we just did. We just found our quote-unquote umbrella. That's the biggest the error could ever be. That's as far as we can be away from it. But remember, originally, we were asked to prove, let me get a color to show it, we were asked to prove that that thing was less than 1 over 700. Well, 1 over 720 is smaller than 1 over 700. So, by the transitive property, we've shown it's smaller than something that's smaller than 1 over 700. That means we are done, and we have completed the problem. Our job, our task here, was to find the alternating series error bound, which we did by looking at the next term and plugging in the appropriate x value. Once we had that term, we just had to show that the original magnitude of that error was less than that value of the error bound, and because that value was naturally smaller than the number we were asked for, we have completed the problem. It feels very strange. It probably feels like what were we even doing? We were just trying to work through to find what that next term was, and then to cap the error and say, well, if it's this small, it's obviously small enough to meet the criteria we were looking for here, to show that that magnitude of the error is small enough, sufficiently small. There's a phrase I wanted, sufficiently small. So there it is. Now again, if that worked for you and you're like, yeah, cool, okay, got it, then you're awesome. If you're not, I totally understand that. It's hard to talk about, let alone to try to get into someone's mind. So this is probably going to be one of those topics where as you're working through the problem set, you'll probably want to reference this document, to reference this video a few times just to get a feel for it. Now, you're welcome. I guess the one, what is a positive that comes out of a massive global pandemic? I guess that this topic isn't included on the AP exam this year. I guess you can be happy about that. I don't know, find silver linings where you can. But in any event, like, there it is. There's our first alternating series error-bound example. I did create a second one, though. I thought that it would be appropriate to look at a second example and to create one here that would help you just kind of see this in action one more time. So in our second example, we're told to let p sub 3 of x be the third Maclaurin polynomial for sine of x. And in fact, you know what? I can already do that. Like, I know exactly what that is, so I'm not even going to read the rest of the problem. I know that sine of x is equal to x minus 1 over 3 factorial x to the third plus 1 over 5 factorial x to the fifth minus some stuff, and then plus that toggle times x to the odd power over odd factorials. So I know what that is. So let's start right there. Because of that, if we want the third Maclaurin polynomial, p sub 3 of x is going to be equal to x minus 1 over 3 factorial x to the third. So am I going to use this? I don't know, but I just wanted to get some stuff out of the way because I know some stuff about this series. So let's let p sub 3 of the third be the third Maclaurin polynomial for sine of x. Way ahead of you, bud. Then asks us to find the alternating series error bound for approximating the sine of 1 over the 5th root of 10. Who writes these? Oh, I do. Never mind.
I didn't pee my pants. That was so funny.
Yeah, I can't be angry at the problem writer when that would just be me staring in the mirror. But hey, being alone, stuck home alone, I just talk to the mirror all the time. So, yeah. Anyway, so we want to approximate this thing. So we're trying to find what value is going to cap this particular one using p sub 3 of x. So let's start by just kind of writing this out. I want to maintain that same notation that we've been using here. So following through here, if we want to talk about the error when using a polynomial of degree 3 to approximate a value of, at x equals the 5th root, 1 over the 5th root of 10, that is of course going to be equal to the magnitude of the difference between sine of that value and p sub 3 of that value. So that's what we're looking at. And then our question is, of course, what is that less than or equal to? We want to figure out what goes here. So our task in this problem is determining what number goes right there. So we want this thing, which is the alternating series error bound. ASEB. Okay, so having said that, let's do this. We know that that thing that we're calling the alternating series error bound is going to come from the absolute value of the next term. So this is exactly the way I set this thing up. Absolute value of the next term. Well, since we're talking about the third degree polynomial here, the next term is actually going to be this one. So truthfully, this is going to be pretty easy. We have that the next term is going to be, and we'll do the magnitude, 1 over 5 factorial times x to the 5th. Now, of course, we need to be a little bit more specific than that. We were told what the x value is that's being plugged in here. Like, this is all key for the fact that we're using x equals 1 over the 5th root, or 1 over the 5th root of 10. So what we need to do is we need to evaluate this expression at x equals 1 over the 5th root of 10. So having done that, I'll move this down here. That's going to give me as my magnitude, and I can see it's all positive, so I don't need to worry about the absolute values anymore. We'll have 1 over 5 factorial times that thing to the 5th, and of course what we're plugging in is the x value, 1 over the 5th root of 10. When we multiply this out, 5 factorial is 120. We also have 1 over the 5th root of 10 to the 5th power, which is just 1/10, and that means that our value is equal to 1 over 1200. And this value we just found is our alternating series error bound. So we don't have to go back and make any sort of statement because we weren't asked to show that some particular error bound was sufficient. Like we don't need to show this is sufficiently small. What we just did was we found the largest possible error. Wait, let me make sure I say this correctly. Yeah, we found the largest possible value of that error when we approximate with this third degree polynomial. So you can see, approximating this sine value, and 1 over the 5th root of 10 is pretty close to 0, we're pretty accurate. 1/1200, that's pretty decent. That's somewhere in the 3rd or 4th decimal range, so we're doing pretty well at this point. Obviously, if we wanted to be more accurate, we just need to add more terms and get a better and more precise approximation. So there is the alternating series error bound. Let me just write that in here once. This is the alternating series error bound itself. So again, pretty familiar. It's the same thing we did in the previous unit when we dealt with alternating series. So nothing that's particularly out there, I would say, but hopefully beneficial and valuable too. Okay, having gone through that, I've now presented the entire alternating series error bound stuff. So I'd love to give you an opportunity to try this out. As always, I'll write out the answers and post them, both in the Google Drive and probably somewhere else once I wrap my mind around all that stuff. With topics that are as weird and uncomfortable as these, If it's something you're really trying to master, obviously not for the AP exam in 2020, but either for future years or just for your knowledge, I definitely think these triads are an essential, crucial part of your work, just so that way you can make sure that you're, that's what I'm going for, that you have your mind around what this computational and calculation looks like and what that demonstration of sufficient size will actually do. So rather than keep talking, I'm just going to let you take a few moments to work through here, and then we'll come right back and we'll look at the other type of error bound that's out there. Okay, so hopefully that was enough time for you to work through those problems and really kind of get into your mind the alternating series error bound idea, both the computation and how to like demonstrate the particular closeness or sufficient closeness. Having said that, I want to jump into the second error bound as well right now. So the second error bound, the name is not written up here, but this is for how this will be our approach if a series is non-alternating. So if a Maclaurin or Taylor polynomial, it does not have alternating signs that toggle back and forth, we'll be able to use this one. Now, our expression is right here. This is the piece you'll want to write down. The name of this thing is the Lagrange error bound. Just like with Maclaurin, I try to put an accent on there, this would be Lagrange. The Lagrange error bound. So the Lagrange error bound is the one we use to handle non-alternating signs. Now, having said that, there's a lot of stuff here that's worth kind of pointing out, I think, just to kind of help you make sense of this. So just like before, it's r sub n of a number. So basically the error when we're approximating a particular value of the function is going to be less than or equal to something. So just as you saw, this will be our error bound. In here, there are a few pieces that stand out as being fairly familiar. The first one I want to draw your attention to is the denominator. Notice that the denominator, n plus 1 factorial, as well as this absolute value of a number minus x to the n plus 1 power, those look just like the n plus 1 term of some sort of Maclaurin or Taylor, actually I should definitely say Taylor, series or polynomial. It's x minus c, because of course the number is taking the place of the x value. So x minus c to the n plus 1 over n plus 1 factorial. So in a sense, it has kind of a feel of the next term too, although it doesn't matter if there are terms that are missing in here. It just wants the n plus 1th one. So we're going to use the next number after whatever degree we're looking at. Finally, the other thing that stands out is of course the bizarre awkwardness of this other element, this other factor that's in the numerator. It says the maximum for z, a member of I, and down below it does say I is an interval that contains that number, but the maximum value of the absolute value of the n plus 1 derivative of f evaluated at some number in that interval. So basically, the easiest way to think about this Lagrange error bound is that it's really just a particular Taylor term. It's almost like the next Taylor term, but in this case, it doesn't matter what terms are actually there. This isn't one that's actually going to show up on the progression necessarily. This is one where we take into account the largest possible size that we could have for a particular derivative on a certain interval, and then we kind of mix that in with the rest of the Taylor expression and structure. So where this comes from, if you're curious where this comes from, I think I'll unhighlight that. If you're curious where this comes from, there is a theorem. It's Taylor's theorem. I definitely could not prove this theorem. I've looked it in books, and I've never felt very successful with trying to do that. So instead, I'll just present it here. As it says, if you've got the ability to differentiate through there, then you can describe the error when using an nth degree polynomial to approximate using this form. So in here, I'd say this is one of those things where we just want to get used to using it for one, like not just reading it, but using it. So I'm going to jump right into the first example of this and try to give you a feel for what this is going to look like, this Lagrange error bound. And here we are. So it says for function f of x with a non-alternating Maclaurin series. So notice that in this problem, by the way, I'll just point it out right now, it specifies for us it's non-alternating. So that way we don't have any questions about it. There's not much other information here, so it's a valuable piece of information. We know that we won't be able to use the alternating series error bound. We're going to have to use this thing called the Lagrange error bound. So for this function f with a non-alternating Maclaurin series, it is known that the magnitude of the fourth derivative of x is less than or equal to 54 for all values of x in the interval from 0 to 1. So they're telling us something here. I'll even underline it in red. They're telling us something about the fourth derivative. So are we going to need that? Well, probably. But for the moment, let's just play along again. Excuse me. We're now supposed to show that the magnitude of the difference between f of 1/3 and the third degree polynomial evaluated at 1/3 is going to be less than 1/28. So a lot of stuff going on in there, a lot of stuff to try to think about. Let's try to break this down just like we did before. So keep in mind, where do we begin? First and foremost, using that information, the x value that we're plugging in this case is x equals 1/3. So for our purposes, based on the definition I gave you, that's the number we're going to be plugging in. So we're interested in an approximation of this series of this function at x equals 1/3. In addition, it tells us that n is equal to 3 here. Because we have p sub 3, that's enough to tell us that we have n equals 3. And then, of course, the fact that we have non-alternating is valuable as well. I'm trying to see if there's anything else in there. Oh, shoot, I forgot one important thing. Yes, the n equals 3 is true. But the important thing to note is that our number is in the interval from 0 to 1, which means this information up here is actually relevant to us. After that, yeah, n equals 3 stays. Definitely need to say that. Other than that, we also have non-alternating, as I mentioned a second ago, which means, as you would expect, we get to use our new shiny toy, the Lagrange error bound. So we get to use that guy. Okay, so having done that, let's start to construct this thing. So I'm just going to first kind of like take the structure. So the first thing I want to do is I need to figure out what the maximum value is of the absolute value of f to the something plus 1 of z. So let's start right there. So since we said n was equal to 3, that means that up here we're going to have the 3 plus 1 derivative, which means we're going to have 3 plus 1 up here, which will of course give us 4. Likewise, following the same basic pattern, we have the absolute value of that number, which in our case is 1/3, minus our center, and since we did say Maclaurin is the series, that means our center is 0. And then it's all being raised to the 3 plus 1 power. And then finally, this whole thing is going to be divided by, it says n plus 1 factorial, which for our purposes, we said n was 3, so it'll be 3 plus 1. So there is kind of the structure of our error bound. So having said that, let's now rewrite this expression. So we've still got the maximum value, but we need to find the maximum value of, now we can see the fourth derivative, and it'll have to be on an interval containing that number, 1/3. Then over here, we're going to have 1/3 to the 4th power. And lastly, we're going to have it all over 4 factorial. So having said all that, this isn't actually going to be too bad for us to work with. The only problem that I see here is that we've still got to deal with this maximum value. And we don't know a whole lot of information about the fourth derivative of a function that we don't even see. There's no information about f here except that it has a non-alternating Maclaurin series and that its fourth derivative is less than or equal to 54. Wait. We know exactly that information. So, oh look, I've already colored it red, in fact. Keep in mind that when we say something like this, the fourth derivative of f is less than or equal to 54, that's the same thing as saying 54 is the maximum. So in a sense, that statement is now telling us what the maximum value is of the fourth derivative of that function. So with that in mind, if we're asked for the maximum, we only need to do it across an interval that contains 1/3. Well, 0 to 1 contains 1/3, which means that this is valid. So rather than kind of pause, let's just do this. Let me change the color before I excitedly do this. Let's go with, we'll go with pink. We just saw that 54 is the maximum right over here. So let's just replace this with 54. Right? Because that's the same thing. We just said 54 is the maximum. We want the maximum of the fourth derivative. Okay, cool, I'm done. There's our stuff. And then having said that, we can then complete what this is equal to. This is equal to 54 divided by 4 factorial, which is 24, times 1 over 3 to the 4th, which is 1 over 81. If we clean this up a little bit, I'll do that right here. If we clean this up, 54 and 81 both have a factor of 27. This becomes 2 over 3. And then 24 becomes 12 when it undoes itself with the 2, which means this is all equal to 1 over 36. So to recap all of that work we just did, we just showed that the absolute value of f of 1/3 minus p sub 3 of 1/3 is going to be less than or equal to exactly what you see right here, 1 over 36. And then our question to ask ourselves is that value sufficiently small? So is that less than 1 over 28? Well, 1/28 is a smaller number, or is a bigger number than 1/36, which means we've shown that 1/36 is smaller than 1/28, which means we're done. The end. Okay, so now I pause for just a second. Let me just point out that the real truth here, the thing that's probably most important for us, is to note that this thing we found, 1 over 36, this is the Lagrange error bound. So just note that that thing that we found, we were asked to show something, so we did have to do a little bit more. But there is that value we were looking for. We found the Lagrange error bound in this case, and it was sufficiently small for us to then make our conclusion. So I might even put a little therefore there just to kind of say, we did it, we're good. Okay, so in this first example, you'll notice that you were given just the right information in order to complete this task. You were given the information about the fourth derivative so that way everything was set up nice and clean and you were ready to go with it. Obviously, that might not always be the case, and that's what our second example is going to dive into. What happens if we don't get just the right information and we have to find that maximum value, say, by ourselves? So let's do that. So our last one is an example that's always been dear to my heart, or something close to my heart. I bring this up because it was on the AP exam that I took, and I made a mistake when I was dealing with it. In my opinion, it probably cost me the 5 that I wanted on that exam. Yeah, fun trivia fact. 5's on the AP Spanish exam and AP Lit exams, but only a 4 on the BC Calculus exam. Got a 5 on the AB sub-score, though. So, yeah, not too shabby. No, I'm just kidding. So anyway, in this problem, we are given cosine of 4x plus pi over 4. So this is all sorts of interesting function. It's got a period shift. I think the period here is what? Pi over 2, so it's really condensed. It's going up and down pretty fast. It's also got a phase shift in here of, I think, negative pi over 16. So it's also shifted a little bit. There's just a lot going on. The questions we want to answer, though, are fairly simple. We want to go through and first compute p sub 4 of x, so compute a particular Maclaurin polynomial. And then afterwards, we want to demonstrate a particular closeness of our estimate using that polynomial, or using a similar polynomial. So in order for us to get there, let's just jump in right off the bat and take a look. So if we want to compute p sub 4 of x, like something that's going to be a little bit of a challenge, we need to go through and be ready to compute a few derivatives. So we're going to go back to the old-fashioned way. We can't plug this expression in as readily to the cosine Maclaurin series because it's not centered at 0. This expression isn't centered at 0 the same way. So let's just kind of kick it off. We'll take some derivatives. It's not necessarily going to be the most difficult work. So we'll start here. There's our f of x. If we want to take the derivative of f of x, of course we know the derivative of cosine is going to be negative sine, but in addition, the derivative of the inside is 4. That means our derivative here is going to be negative 4 sine of 4x plus pi over 4. Following the same pattern, we'll look at the second derivative. We'll do the same thing. The derivative of negative sine is negative cosine, but we've got an extra 4 from the chain rule, so that'll give us negative 16 cosine of 4x plus pi over 4. It's probably one of those parts of the video where I bet people will speed it up really fast. No, something I'm talking like a chipmunk. Yep, I imagine that's what's going to happen. Following the same pattern of chain rule and derivative of trig, we're going to get, I think, positive 64. That'll be sine of 4x plus pi over 4. And then lastly, since we wanted to go out to the 4th degree, if we do the 4th derivative, that's going to bring out one more 4. Geez, okay, we can do that. It's 256, I think. 256 cosine of 4x plus pi over 4. Okay, so there's our first work. Now from here, we're interested in the Maclaurin polynomial. So since it's a Maclaurin, we need to plug in x equals 0. And again, I'm going to be a good student, since most of you are probably speeding this up at this point, if you're even watching it. And I'll do that. And then I'm going to see what those values are, and then I'll finally take into account the factorials. So in here, something important to note, by the way, it's probably in the back of my head, is obviously we're going to be evaluating some trig values here. Cosine of pi over 4, sine of pi over 4, both of those are root 2 over 2. So we'll just take that as a given. So in here, this first one, we're going to get root 2 over 2. The second one, we're going to get negative 4 times root 2 over 2. Third one will be negative 16 times root 2 over 2. The next one will be 64 times root 2 over 2. The next one will be 256 times root 2 over 2. And then we also need to take into account the factorials. Obviously, the first ones we're just dividing by 1. So that first one just becomes root 2 over 2. Second one is going to be negative 2 root 2. The next one we divide by 2 factorial will be negative 8 over 2, which is equal to negative 4 root 2. Oh, shoot, by the way, did you just notice something? Plus, minus, minus. This is non-alternating, everyone. Oh no, we can't use the alternating error bound. Divide by 3 factorial. You forgive me if I just take advantage of the fact that I already did this problem. I don't want to calculate that whole thing out. It's going to be equal to 16 root 2 over 3. And then when we divide that last one by 4 factorial, that's going to be equal to 16 root 2 over 3 also. So there are our coefficients. So having done all that, we can write out our polynomial. P sub 4 of x is going to be equal to, it looks like root 2 over 2 minus 2 root 2x minus 4 root 2 x squared plus 16 root 2 over 3 x cubed and plus 16 root 2 over 3 x to the 4th. So there is our polynomial. We're in great position. Okay, so we found P sub 4. No error bound so far. Well, that's about to change. We now want to show that the 6th degree, ooh, interesting, the 6th degree when approximating at 1/4 is going to be within 1/4200th of the actual answer. So, it's going to be quite a bit. So where can we begin? Let's begin by just stating the Lagrange error bound. So what do we know here? We know r sub 6 of 1/4 is going to be less than or equal to, let's include all the parts, less than or equal to the maximum value of the, let's make sure we think this through, if we're using the 6th degree to approximate, this is going to be the maximum value of the 7th derivative of f. We'll multiply times the absolute value of 1/4 minus the center, which was 0, all raised to the 7th power. And then finally, we'll put this whole thing, we'll put this whole thing over 7 factorial. So again, if you're not sure where those things are coming from, I'm taking advantage of the fact that because 6 is our value right there, that means n plus 1 is going to equal 6 plus 1, which is 7. So I'm just taking advantage of all that stuff. If I want to, I could clean this up just a little bit, but obviously, I actually think I'm going to hold off. And the reason is, if there's one thing in here that's going to be a problem for us, it's going to be that maximum value of the 7th derivative. So our real question, our real task here, is to figure out what is the largest value the 7th derivative can have. On any interval, obviously one containing 1/4, but really on any interval I think would be valuable info. So let's think about this. What do we know? Well, let's see, the things that we do know. Like we're talking about the 7th derivative, but let's go back. We just did the 4th derivative. We saw that the 4th derivative of x was equal to 256, and I think it was cosine? Yes. Cosine of 4x plus pi over 4. So we saw that. So that's something that we had. Now, from here, if we want to do the derivative again to slowly get towards the 7th derivative so we can start to analyze it, it's worth pointing out that the 5th derivative the fifth derivative of x is going to be 4 times 256. And then, of course, we'll have a negative because it's the negative cosine, the derivative cosine. Geez, sorry. This is just annoying to have to write out. So we'll have this as our fifth derivative. So having said that, at this point you might want to notice that it's not going to actually help us to keep multiplying by 4 and trying to figure out what that big value is. Sure, we could do it. What's this one? 5, 12, 10, 24. I think it would be easier for us to go through and actually just find a good way to express this. So let me take a step back for a second. Let me point out this. In the first f of x, we had 1 as our coefficient. That's 4 to the 0. Then we had negative 4 to the first. Then we had negative 4 to the second. Then we had 4 to the third. Then we had positive 4 to the fourth. So at this point, it's probably worth pointing out we get negative 4 to the fifth. And if we go take the derivative to the sixth order, we'll have, it looks like, let's see, negative 4 to the sixth times cosine of that stuff. And then the question that we've really been after this whole time was all about the seventh derivative. So let's take advantage of it. The seventh derivative we should also be able to find. The seventh derivative, following the same pattern, is going to be equal to positive 4 to the seventh times times sine of 4x plus pi over 4. Now that was a lot of talking and differentiating and chain ruling and pattern building. And the question that you might have at this point was, why did we spend so much time trying to find that? Like, what's our ultimate goal here? And the ultimate goal is this. If we know what the seventh derivative of the function value is, if we know the seventh derivative is, for instance, 4/7 times sine of something, we can actually find its maximum value. So let's go do that. This is f of x. We want to this is the seventh derivative of f of x. What we want to figure out what is the maximum value of this. Like, what's the biggest that ever gets to? Because that's really the question. So for us, if we want to figure out what the largest value is of the seventh derivative, that's not actually going to be difficult. Because let's look at the maximum value of the sine curve. We have 4 to the seventh times sine of stuff. So I don't mean to downplay the stuff, but I just want to focus on something else. Here's the thing. Sine, what do we know about sine of x? Well, sine of x, its magnitude is always less than 1. In fact, less than or equal to 1. It could be equal to 1 at its maximum. So if that's true, and we want to talk about the maximum value of something times sine, we can just make a substitution and just say, well, that maximum is going to be equal to, the maximum value is going to be equal to 4 to the seventh times 1, which means the maximum is actually equal to 4 to the seventh power. That's a huge step for us. Now that we know the maximum value, we can set up and find the Lagrange error bound. So let's do that. We said the Lagrange error bound was going to be this guy. Oh, look, I can even bring it down. It actually helped me this time. That's going to be our Lagrange error bound. Well, let's make our substitution and dig in. This is going to be equal to, we have this massive fraction. Obviously, it's going to be over 7 factorial. Like, that's not changing or going anywhere. Oops. Next, we have the maximum value. Well, we said that the maximum value right here is going to be equal to 4 to the seventh power. Because we knew sine's maximum value was 1, so 4 to the seventh was the coefficient. That means the largest value is 4 to the seventh times 1. Likewise, we can now multiply by 1/4 to the seventh, which is going to be, well, let's think about this. 1/4 to the seventh is 1 to the seventh over 4 to the seventh. Look at that. Yes, these problems, I feel very proud every time I finish one of these problems because constructing them takes me forever. I have such a hard time with these problems. We'll go orange again. I'm enjoying orange. There it is. So what I notice is 4 to the seventh and 1 over 4 to the seventh multiplied to 1, which means the error bound is 1 over 7 factorial. Do you know what 7 factorial is? Because I do. It's 1 over 5040. So having said all that, what has that just done? Where are we at here? What have we accomplished? Well, what that means, that's weird. What that means is we can now state that the magnitude of the difference between p sub 6 of 1/4 minus f of 1/4, whatever that function value happens to be, is going to be less than or equal to our Lagrange error bound. And by the way, that is the Lagrange error bound. We just found it. I wish it had just been kind of sitting on the floor and I could use my little grabber to pick it up. That would have been much easier than all of this. But at the same time, we found it. So there it is. So that means that difference, the remainder, that's what the difference is, the remainder or the error, is less than or equal to 1/5040. But remember, our goal, as we said at the very beginning up here, our task was to figure out, is that less than 1/4200? Are we accurate enough to meet that threshold? And of course, 1/4200th is a larger number than 1/5040th, which means we've shown it's sufficiently small, which means we're done. So obviously that was not an easy path. This was quite an adventure. This is a much harder problem. Obviously in 2020, I'm not going to give you a question at this level, although I have in the past years. Probably not going to include this on your exam at all in 2020. Future classes are watching this, don't think you're getting out of it, barring a global pandemic. But having said that, we're still able to prove it. The difficulty here was probably just in getting used to that formula, but I'd say the real difficulty was in having to execute a whole bunch of chain rule work and then analyze that sine curve to find its maximum value, all kind of at the same time. So keep that in mind. But basically you've seen kind of the best and worst that the Lagrange error bound has to offer. We had that first example where it's like, hey look, here's all the information you need to finish. And then you had the one where you had to grind through 2 pages of beautifully colorful stuff in order to get to your value. So yeah, there you go. So having said that, I want you to play around a little bit with the Lagrange error bound. There is an error, by the way. It says capital G. There should not be a capital G up there. That's my bad. Having said that, though, there are 2 good problems here. I think they offer you kind of some experience with some different ways to ask and answer the questions. Got 2 different contexts. One asks you for the Lagrange error bound. One asks you to show a particular bounding is true. Gives you something graphical as well to look at. There's some interesting stuff in here. Basically, I'm going to... a graph that's just not quite good here. Hold on. I'm going to obviously let you work here. Should have labeled this stuff. I apologize. This is the 4th derivative of x, and this is values of the 4th derivative. Okay, I apologize. That graph was just not enough. I'll put 0 there too. Okay, so having said that, like having given you all that, please do take a few minutes to work through. There's no more lesson after this. It's just when you come back, I'm just going to make a couple statements and call it a day from there. So once you've taken a look, jump in and come right back and we'll wrap this puppy up. Okay, hopefully that was enough time for you to work through those triads wherever you happen to access them. To wrap things up, I just want to kind of bring everything to a conclusion really fast and end this thing as much quickly as I can. Truthfully, this lesson would have gone so much faster in class just because being able to answer your questions is a lot easier than trying to cover every base. And also I kind of go crazy on all the colors here, I think. So anyway, what I want to wrap this up as is just by pointing out kind of the futility of this whole thing. The truth is, this whole concept of error is basically worthless to us at this point. We have graphing calculators. We have Desmos. Like we have, just look how easy it was for me to find cosine of 1. I just typed in COS1 and Desmos spit out the answer for me. A free website that's like one of the world's most powerful graphing calculators. Having said that, this is just kind of an exercise for us. It's for the purpose in 2020, it's just to wrap up the unit the same way I would normally. It's a topic that's very narrow in when it gets used, like when is the right time to use it. It's always telegraphed pretty well too. You're always trying to show something, you're trying to cap something or find a particular error bound, but it's an idea that's just kind of endured through the years, even though it's not necessarily needed anymore now that we have high-powered, powerful computers literally in our pockets at all times. So just keep that in mind. If this topic doesn't stick with you, that's actually okay, especially in 2020. Because it's not included on the AP topics for this year, so you're not going to be assessed on it there. And as I said, in 2020, I'm definitely not going to assess you on this either. I just know that there's no replacement for being able to practice this in class. So having said that, though, just as kind of a quick recap of what we've talked about in here, Let's go back to the beginning at the very beginning, or from the start. When we started out, we talked about and reminded ourselves of the fact that really the value in a Maclaurin or a Taylor polynomial or a power series is the ability to approximate a transcendental function's value without needing a fancy calculator. The thought process being that when you turn something into a polynomial, it's easy to compute function values for it. And obviously, if you get a much more accurate polynomial, you get a very accurate estimate that, maybe not super easy to calculate, but much easier when you have just numbers and powers. So from there, what we wanted to do is we wanted to answer in today's lesson the question, how accurate is a particular estimate? If we use a certain number of terms from the Taylor to approximate a particular function value, how good of an estimate are we actually getting? And God, why couldn't I have just said that in the beginning? I feel like I talked for 5 minutes without saying those exact words. But that's what we wanted. We wanted to find like a cap. We wanted to find a threshold that says this is the worst or the furthest off our answer could be, given this polynomial and estimating this function. So first we talked about the alternating series error bound, which was a familiar foe. It was something we'd seen in the previous unit a little bit. It was just the magnitude of the next term. The biggest challenges here were, of course, we had to plug in the particular x value. We had to read a lot of stuff in the problem. Otherwise, it was just literally what's the next term, take its absolute value, plug in the x value, and there is our, quote, alternating series error bound. We did a couple problems with that, one finding one going forward. After that, and you trying it, we talked about the other one, which is what happens if our series or Maclaurin polynomial or Taylor polynomial is non-alternating. So if the signs don't toggle back and forth, we have what's called the Lagrange error bound. And the Lagrange error bound looks just like a term of a Taylor polynomial. The only difference, like the biggest difference is, of course, we've got this maximum value of the n+1 derivative, and it doesn't matter what terms are actually in there. We just use the next degree or the next order no matter what. After that, we did two examples. One where it was very convenient and we were told all the information we needed to compute the Lagrange error bound easily. And the other, I made us work for it. And I was going to say I made you work for it, but truthfully, I was the one that was doing all this grinding. Although, once again, that just looks really nice. That's like aesthetically pleasing. I think my handwriting and color choices have become really on point through this sucky hiatus. Anyway, having said that, that completes our lesson, including with the try it. Hopefully, no matter what, no matter how strong you feel with these topics, hopefully you had some exposure to the idea of an error bound and the ways and times you can use it. That's probably the only thing I would ever consider asking is which one do you use for which series. But in any event, with the second big unit of Calculus BC done, thank you for watching. Thank you for humoring me as I wear my cowboy hat. Is that even an appropriate accent? I don't know. I sound like Elvis at this point. I'm just going to stop. I'm just going to say thanks for watching. Obviously, I miss you. I would rather be entertaining you in class than speaking to this lovely webcam. But no matter what, I hope you're well. Hope you're safe. I miss you. And thanks for watching. Bye.